Hey everyone, and welcome! Today, we're jumping into a really important topic from 3D geometry, the equation of a line in space. Now, I know that sounds a bit intimidating, but trust me, it's way simpler than you think. By the end of this, you'll be a pro. So, let's get right into it.
But before we hit the formulas, think about this for a second. In a game like BGMI or Valorant, when you shoot, how does the bullet travel in that perfect straight line? Or when you're using Google Maps, how does it draw that straight highway path for hundreds of kilometers? Well, that's all about defining a line in 3D space, and that's exactly what we're going to master today.
So, let's start with the main idea, and believe me, it's super simple. To define any straight line in the entire universe, you only need two things. Just two basic ingredients, that's it.
So what are these two key ingredients? First, you need a single fixed point that the line definitely passes through. Just think of it as your starting address, or maybe your spawn point in a game. And second, you need to know which way the line is going, its direction. That's the road you have to follow. A starting point and a direction. That's all you need.
You know, this should actually feel a little familiar. Back in class 11, when you did 2D geometry, you used a point and a slope, right? Well, now, in 3D, we just have to level up our game. A simple number like slope isn't enough to describe a direction in 3 dimensions. So we replace it with something much better, a direction vector. But look, the core idea is exactly the same. Point plus direction.
Okay, so how do we actually write this down using math? Well, there are two main ways. Let's start with the first one, which I like to call the live GPS tracking method. Its official name is the vector form.
And here it is, the vector equation of a line. Just look at how simple and clean that is. Vector r equals vector a plus lambda times vector b. This tiny little equation is literally a live GPS tracker. It can tell you the exact coordinates of any point on that infinite line.
Let's break it down using our GPS idea. Vector A is the position vector of your known starting point. Think of it as a fixed address. Vector B is your direction vector. That's the road you're traveling on. Now, this new symbol, lambda, is just a number, a scalar. It basically tells you how far you've traveled along that road. And finally, vector r is your current location. If you change lambda, you change your location r along that line.
So to visualize it, it's really this simple. To find your current spot, r, you just start at your initial address, a, and then you travel for some distance, lambda, along the direction of the road, b. Your destination is just your start point plus your journey. That's all the formula is saying.
Now here's a very, very important tip. So many students get confused between vector A and vector B. Please remember the analogy. A is a fixed address, a point, a location. B is the path, the road, the direction. The vector that gets multiplied by lambda is always the direction vector, B. You can't live at a path, right? You live at an address.
All right, so the vector form is our live GPS. Now, let's talk about the second form, which I call the printed map. This is the Cartesian form.
So what's the big difference? Well, the vector form, with its lambda, is great for tracking a moving point. But the Cartesian form gives you one single equation that describes the entire line at once. It's like having a printed map that shows the whole road, but without that little blinking blue dot that shows where you are right now.
So how do we get this printed map from our GPS? It's a really simple three-step process. First, we just write out the vector equation for each component separately, for x, y, and z. Now our goal is to get rid of that parameter, lambda. So for step 2, we just do some simple algebra on each equation to get lambda by itself. And since at any single point on the line, lambda has to be the same value for x, y, and z, well, we can just set all three of these expressions equal to each other.
And boom, when we do that, we get this beautiful symmetric equation. This is the Cartesian equation of the line. See how it's structured? The coordinates of our known point, x1, y1, and z1, are up top in the numerators, and the components of our direction vector, a, b, and c, are sitting down in the denominators. No more lambda, just a clean equation for the line.
Fantastic. Now that we know both the vector and Cartesian forms, let's quickly look at the two main types of problems that you are going to see in your exams.
Okay, scenario 1 is the easy one, the direct one. The question gives you a point and it gives you a direction vector. You just put them into the formula. It's like your GPS already knows where you are and which road to take. Scenario 2 just adds one small extra step. The question gives you 2 points on the line, but it doesn't tell you the direction.
This is like telling Google Maps your start and end point, and it has to first calculate the road that connects them.
So please, please burn this into your memory. Whenever you see a question that gives you 2 points, your first job, always, 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 is to find the direction vector of the line.
And how do you do that? Oh, it's incredibly easy. If you have 2 points, A and B, with position vectors A1 and A2, the direction vector B is just their difference. Position vector of the second point minus the position vector of the first. Once you've calculated this B, you now have a direction. And you can use either point A or point B as your starting point. And just like that, you've turned a Scenario 2 problem into a super easy Scenario 1 problem.
Okay, just one last skill we need. What if we have to go in reverse? What if a question gives you the printed map, the Cartesian form, and asks for the live GPS, the vector form? Let's quickly see how that's done.
This is probably the easiest thing we'll do all day. You just have to read the information right off the equation. The point x1, y1, z1 comes from the numerators. Just be really careful with the signs. The standard form is x minus x1, so the coordinate is positive x1. And the direction vector's components, a, b, c, are just sitting there in the denominators. Once you pull out vector a and vector b, you just plug them into our good old vector form, r equals a plus lambda b. Simple. All right, let's do a super fast recap. First, every line in space needs just 2 things, a point, A, and a direction, B. Second, we have 2 ways to write it. The vector form, our GPS, is r equals a plus lambda b. And the Cartesian form, our map, is x minus x1 over a equals y minus y1 over b equals z minus z1 over c. Third, if a question gives you 2 points, your first step is always to find the direction b by subtracting. And finally, just remember that both forms are telling the exact same story, just using different languages.
Seriously, you've got this. Don't get overwhelmed by the different-looking formulas. Every single problem about the equation of a line boils down to one simple mission. Find the point A and find the direction B. If you can find those 2 vectors, you can solve anything they throw at you.
And I'll leave you with a little something to think about. We just saw that a line, which is a 1D object, needs a point and one direction vector. So, what 2 ingredients do you think you would need to define an entire plane, which is a 2D surface, in 3D space? Think about that, and we'll cover it in our next explainer. See you then!